Thank you so much for joining us, guys, for this awesome session today on electric circuits. So everyone that does physical science, make sure you guys have your calculators ready. You've got your formula sheets ready. You've got pen, you've got paper. As you guys know, there's a lot of calculations in this section, and we're going to get it done and make it easy for you guys to understand. All right. Just a massive thank you to everyone that's joined us in the Zoom community, the Glow Institute team. Thank you very much to the guys on TikTok. Remember, guys, it's an interactive session. Please remember, as you engage and as you guys have been engaging every day, I'm going to keep reminding you, post in the chat, use your Zoom reactions for us to interact. If you've got people that you know should be in this session right now that are not in here, send them a quick message, say, guys, come through, the session has started, let's get going. Awesome. Without wasting more time, I'm going to jump straight into my session. Let me just check if Theo managed to get back on. Theo, are you back?
Yes, Ernest.
Thank you so much. Okay, no, great. All right, cool. I'm jumping straight into my content for the day. Let me just get my whiteboard up. Give me 2 seconds, guys. Okay, Theo, just confirm if you can see my whiteboard.
Yes, I can.
Fantastic. Okay, so I'm going to just switch my video off for the duration of the session. I'll put it back on at the end when I'm done with all my presenting and everything, right? Cool. So today we're touching on electric circuits, right? And as usual, I'm going to start us off with just some theory, going through some of that theory, the things we should remember about this topic, and then we're going to go into some practice questions that we can then all do together, right? So let's get started. Electric circuits, let's first do some basic definitions. So what I mean by basic definitions, guys, please don't annotate on the whiteboard. It's distracting for everyone. It appears on everyone's screen, not just yours. So basic definitions, current is the rate of flow of charge, right? Where I, which is our current, is equal to Q, which is our charge over change in time. This is measured by an ammeter. Ammeters are connected in series and the resistance is very low. That's why you can connect them in series. Then next up, we're going to look at potential difference, right? So potential difference is the energy required to move a coulomb of charge between 2 points. So again, that is V, which is our potential difference, is equal to W, which is our energy or work, over Q, which is the charge we're going to be dealing with there. This is measured using a voltmeter, right? Voltmeters are usually connected in parallel. You can see there that voltmeter will usually look like this. It's circle with that V on the inside. The resistance of a voltmeter is usually very high. Then we connect them in parallel. Little to no current flows through there. Usually for the purposes of what we're doing now, we assume that no current flows through a voltmeter. That's why they'll usually say a voltmeter of very high resistance, right? That is to remind you that no current is going to flow through that voltmeter. Okay. And then again, resistance is the extent to which the flow of current is opposed. Basically, how hard is my current being opposed, the flow of my charge, right? And then lastly, in our little definitions there, we're looking at EMF, known as our electromotive force, right? Now that's basically what makes our electrons move, right? So therefore, it's the force that makes electrons move. By definition, if you think about it this way, it's the energy provided per coulomb of charge that moves through the cell. So an EMF of 6 volts basically means that I've got 6 joules of energy given to each coulomb of charge that flows through my circuit, right? That's how we can think about that one there, which brings us then into Ohm's law, right? So again, Ohm's law, the current through a conductor is directly proportional to the potential difference across it, provided temperature remains constant, right? So when temperature remains constant, that's when I am following Ohm's law. If the temperature isn't kept constant, and then I'm not going to follow Ohm's law, and then I end up with what I call, or what are called, non-ohmic conductors. So example, the filament of a light bulb, right, is a non-ohmic conductor, but a piece of copper wire, that is an example of an ohmic conductor. And you can see there, the ohmic conductor, the line that it forms there, the V over I, is going to be quite consistent. What is the V over I? The gradient of this graph. So if you think about it this way, V over I, let me just make that a little bit smaller so you guys can see it. V over I is equal to R, right? So which means in this case, the gradient of this curve talks about the resistance. And then an ohmic conductor, you're going to have constant resistance across the board. Whereas then a non-ohmic conductor, what ends up happening is that then this happens because as the temperature changes, the resistance of that particular thing will change as well. Okay, and then next up, let's quickly move and look at resistors and how resistors move in series, how resistors move in parallel, and how we work that particular thing together. So when we're dealing with resistors in series, right? Resistors in series, how do we add the resistors, right? How do we add the resistors and sum them up? So given the example of what we've got there, I've got 3 resistors, 2 ohm, 4 ohm, 10 ohm. When I want to add my resistors in series, I'm going to simply go R1 plus R2 plus R3. And that's how I add resistors in series. Okay. Now, what about the current when resistors are in series? So the current when resistors are in series will be the same. So the current through the 10 ohm is the same current through the 4 ohm, the same current through the 2 ohm. So current remains the same in series, but my voltage is going to split, right? And what we can see there, my V total is equal to V1 plus V2 plus V3. So basically, when you guys get to university, you'll learn about, they usually refer to it as Kirchhoff's volt laws and Kirchhoff's current laws. In this case here, we can see it's a little bit of Kirchhoff's volt law in action. They don't necessarily call it that in varsity, in high school, but you can see that I've got the volt reading around here, voltmeter reading around there, voltmeter reading around there. If you add those up, it's going to equal to the voltmeter reading across the entire space, right? So V total is going to be equal to the sum of all the voltages or the potential differences of each of the resistors within that whole space. So in series, my current remains the same across and the voltage is going to be split in series. Hope that makes sense. All right, now let's quickly look at resistors in parallel. In parallel, let me quickly go down there. Resistors in parallel, we normally refer to these as our current dividers, right? Now, how do we add resistors in parallel? We're going to use this formula right here. And that formula over there, R parallel is equal to 1 over R1 plus 1 over R2 plus 1 over R3. That's when we've got resistors that are in parallel, right? And in that case there, we need to say that 1 over R parallel is equal to 1 over R1, 1 over R2, 1 over R3. So that was a little mistake there. This is supposed to be, let me quickly fix it on the screen. That's 1 over R parallel is equal to 1 over R1, 1 over R2, etc. Just like that. Let me write it a little bit neater. Then we can quickly have a look at it together. There we go. 1 over that is equal to 1 over all of those there. Now again, where R1, R2, and R3 are the resistances of each of the branches of the parallel. So what do I mean by the branches? So when you look at a parallel combination, a branch is basically, here comes current, it branches 1, 2, 3. Those are 3 different branches. So here's one branch, here's another branch, here's another branch. So when I say R1, R2, R3, what I mean is that R1 is going to be the resistance of anything in branch number 1. So there, branch 1 is going to be 2 ohms plus 6 ohms. Then maybe I've got branch 2. So branch 2 is going to be here. So then R2 is going to be 4 ohms. Then finally, I might have branch 3 here. And then in this case, R3 is going to simply be 8 ohms, right? And then we look at the branches that way. So in a branch, if you've got series within one branch, we then add those series ones together. And then we can do R total by saying 1 over R1 plus 1 over R2 plus 1 over R3. And that's going to be equal to 1 over R total. Hope that makes sense to you guys. And then one key thing that we need to remember here is the more branches we have, the less effective the resistance, regardless of the resistance in each branch. What that basically means is that as I add more and more resistors, right, in parallel, my total resistance goes down. As I add more and more resistors in series, my total resistance goes up. So it's very important. The more resistors I add in parallel, the less effective my resistance becomes, meaning my R total will go down in that case there. So there's a very important one about resistors in parallel. Now let's quickly have a look at power And then finally, we're going to look at internal resistance, right? So power, it's the rate at which work is done. In this case, we're talking about electrical work, right? The work that the current is going to do as it goes through any kind of electrical component, the resistor, a light bulb, anything like that. So example, how quickly electrical energy is turned into light and heat by a light bulb, etc. Therefore, more power equals a brighter light bulb, right? Very important. When they ask you questions like, what's going to happen to the brightness of the light bulb? One thing you must ask yourself is, what will happen to the value of the power? And how do we calculate power? By using the following equations down there. So remember, by definition, power is the rate at which work is done. What do I mean by that? It's going to be work over change in time. But then you can use the equations down here at the bottom, where we know that power is equal to I squared R. Another version of power is V squared over R. And then finally, another version of power is V times I. Either of those will work. Just make sure you know what is required of you, right? Maybe you have a value for resistance, you don't have a value for current, and then you can maybe use V squared over R, or you've got current and resistance, and then you use I squared times R, or you only have potential difference in current, then you use VI. At the end of the day, use what you've got, use what has been given to you to be able to solve some of these problems, right? Fantastic, guys. Hey, Theo.
Dumelo says, please repeat the part of light bulb.
Not a problem at all. I'll do just that with Dumelo. So with Dumelo, what we can note here is more power equals brighter light bulb. So what that means, right, for those kinds of questions where they'll ask you, what would happen to the brightness of the light bulb if change 1 or change 2 or change 3 is made? What you're required to do for questions like that is figure out what is going to change with the power output. How is the power output going to be affected? So look at then how does the change in current or the change in voltage of the system, right, change the power? If the power output of that particular device or light bulb or resistor goes up, then the brightness will go up. If the power of that goes down, then the brightness will go down. That's just a way to remember when they ask you, how does the brightness get affected? Think about how the power will get affected. Okay, very, very important. And then last part of our quick little intro for the day before I give you guys your first question is looking at internal resistance, right? So internal resistance, we're thinking there really about energy needed to move current through the cell itself. Remember, the cell has to move current through itself, and there's amount of energy that's required to do that, right? It's a little bit of resistance and that you find inside of the battery, so that when a battery creates maybe an EMF of 9 volts, you don't get 9 volts out completely, because some of those volts are going to get used up inside. We usually call those lost volts, right? So let's quickly have a look at this now. And it says some of the EMF used to move the current through the cell, V internal, right, or our lost volts. The rest is used to the external circuit. That's going to be our V external. Then when we can look at our equation there, we can see that EMF is broken down into the energy that makes it out of my cell, right? That's going to be my V external. And then the energy that also, let's say the energy that makes it out of my cell. Let me quickly fix that. There we go. And basically what we can write that as, we know Ohm's law, V is equal to I times R. Then you also have the energy that is used to get the current through the battery itself. That's going to be our V internal, or sometimes we call that our V lost, our lost volts, right? So since V external is equal to IR and V internal is equal to I times small letter r, where small letter r is going to be our internal resistance, we can then use this one here, this equation here. Let me quickly highlight it for you guys. EMF is equal to I times R plus R. That's usually a very useful equation, especially when they come to ask us about EMF and how EMF responds and reacts, right? So that's a great equation that we can use over there. So that's dealing with internal resistance. A very important thing that we need to note also with internal resistance. Whenever your switch somewhere in your circuit is open, right? If my switch in my circuit somewhere is open and I've got a voltmeter, all right, let's say I've got a voltmeter over there over my battery. With my switch open, my voltmeter is going to give me the reading of EMF. Very, very important, right? With my switch open, I'm going to get the reading of EMF. But if my switch were to be closed, so let me quickly, in green, close the switch over here. When my switch is closed, the reading on that voltmeter is going to be V external, not the EMF. And V external basically means it's going to be the current through my battery times the voltage used across the entire circuit. All right. Okay, cool. She is king on TikTok there, says, scrolling through TikTok and came across this live. I swear this is God's doings. It definitely is God's doings. She's king. And if you are going to find value out of the session, please share the live, follow us on TikTok, and then, yeah, make sure you stay tuned for the entire session. We just started and we're going to be live right up until 8 p.m. So you came right at the right time. Okay. And then Theo, do I have any questions on the Zoom side, or can I continue?
Continue, Ernest.
Fantastic. Thank you guys so much. Okay, right. And then when you get given graphs, right, of EMF versus anything like that, what I want us to see there is I'm going to give you a quick little image of how to interpret those graphs, right? Especially when there's internal resistance involved. So we can see EMF is equal to V external plus V lost, or V internal. That's going to be IR times IR. Sorry, I just quickly need to fix some of these. So this is meant to be I capital R plus I small letter r, right, over there for our V external. And then when we look at that together, you can basically say I rearrange the equation. So we can see that if I move my EMF to the right-hand side, move my V external to the left-hand side, and then I change the signs across the board, I've got V external is equal to negative small r times I, which is my internal resistance times my current. That is going to be basically like my MX plus EMF, which is going to be basically like my C. And then you end up with a graph that looks like this. I'm not going to go too much in detail with this unless we get a graphs question. What I want to focus on today is really how do we answer those questions that we get given with electric circuits. And when we've got a graph question, I'll come back to this one and then show you how we basically work that one out. And then finally, to finish off, remember what I showed you guys here. When my switch is open, my V will read my EMF. When the switch is closed, it'll read V external. And in this case, if EMF is 6 volts, have a look here. When I close the switch, my V external will probably drop, right? My voltmeter reading will drop. So that voltmeter that we used to have up here, that red 6 volts will now probably read 5 volts because it's my V external. And the V internal will be 1 volt maybe, or whatever it is, depending on what my internal resistance was. Okay, that's a quick little overview on our electric circuits, right? For that, what I want to do as usual, I'm going to give you guys a question for you to try before we get into our more contextual questions, just to sort of get the blood pumping, get the juices flowing to see how well you guys do. So here's the question 1.8. It says, in the circuit diagram below, R1, R2, and R3 are identical resistors. The battery has negligible internal resistance, right? So it means it's got a 0 internal resistance. The power dissipated by R1 is P. Which one of the following is the power dissipated by R2? I want you guys to have a quick look at that one there. So we've got identical resistors R1, R2, and R3. The power dissipated by R1 is P. Which one of the following is the power dissipated by R2? Remember, for those of you who are joining us for the first time, maybe on TikTok, what I want you guys to do is you're going to literally pick an answer A, B, C, or D once you've done your calculation and just post that in the chat. And the guys on Zoom, do the same thing, post your answers in the chat, and let's see how well we can do. I'm giving you guys 2 minutes for these 2 marks to see what you can do with this question. Go for it. Thanks, Jabu, for posting your answer so speedily. Let's see what we get from everyone else. Okay, I'll give you guys 1 more minute. I've got a B. I got some C's there on TikTok. On Zoom, I'm getting a bunch of B's, B's, almost all B's there on Zoom. Okay. And then I'm getting mostly C's on TikTok and a bit of B. So let's see how this actually works. Okay. 30 seconds left, guys. Okay, I'm getting some more B's on TikTok. 15 seconds to go. If you've just joined the live, please just look at the question on the screen and make sure you can give us an answer that we can then utilize. Five, 4, 3, 2, 1, and time is up, right? Fantastic. Thank you guys for all the answers. Thank you guys for jumping straight in there. Let's have a quick look at what the answer is going to be, right? So what I want you guys to do, let's think about the question. So they've given us identical resistors, so the resistance will be the same. The battery's got no internal resistance, right? And the power dissipated by R1 is equal to P. So R1, the power by R1 is equal to P, right? And how does that look? So the power by R1 is going to be using any one of our equations. So if we look back at our equations for power, let's quickly go there. Power, we have I squared R, we've got V squared over R, we've got VI, right? So let's look at maybe how it's going to affect each of those things. I squared R, V squared over R, and VI. So in this case here, let's assume the voltage out of this cell here. All right, let's call that V. Okay. And then we've got R2 over R3 in that case there. So how is my voltage, right, or my potential difference going to be split across all of these things? Number one. How is the current going to be split? Number two. So let's first look at potential difference. So potential difference, we're going to get a certain value. Let's call this V2 value there. And then there'll be a value here. Let's call that V3. And then if we put a V4, V4 will be exactly the same as V3, right? Then if we look at current as another measure, so I'm going to have current going through here. It's going to split. When it splits, I'm going to have some of it going through here. I'm going to have another bunch of current. Let me pick another color, orange, some other current going through there, and then it'll rejoin and form the purple current again, right? Going right back here. So one thing I know about the resistances, right? The resistors are all identical. So we know that the resistances R1, R2, R3 are all identical. So I know when I calculate power, I'm probably going to use resistance as one of my measures, because it's an easy one to do. Another one that's easy to do is actually using current, right? So when I use my current, what I'm going to do there is I can look at the current through my different cells, the current through my different branches as well. And then what I'm going to do with that one there is I can say current through R1, let's call that just A, right? So the current through R1, I'm going to just call that A. When it gets to that branch of R2 and R3, remember, current splits to the ratio of my resistors. So the most current will go to the smallest resistor, the least current will go to my biggest resistor. But in this case, we're told that R2 and R3 are equal in resistance. They were all identical resistors, which means my current is going to split equally. Therefore, now I can actually tell that my current, let's say I2, the current through resistor number 2, is going to be equal to half A. And the current I3, which is going to be the current through resistor number 3, is also going to be equal to half A, because it'll split half A one way, half A the other way. So now I've got a measure of my resistance, I've got a measure of my current. So let's look at now how we can work this out. The power dissipated by R1 is P. Which of the following is the power dissipated by R2? So let's go and work that out. R2, so the power dissipated by R2, we've got R and I. If we go work out the power for R1, we said we're going to use resistance and current. That's going to be I squared R, where the I in this case is going to be A. So power is going to be I squared R. So it's going to be A squared. We're just calling it A squared times the resistance of everything, which is R. Now let's look at R2. R2 is going to have I squared. What is the current through R2? It's a half A, right? So I'm going to end up with a half A squared times the resistance is the same, just R. If I work that out, half A squared, I need to square the half and the A, right? Which is going to give me half squared is going to give me 1/4. A squared is going to give me A squared times R. Now, if I compare those two, the power within R1 is A squared times R. The power within R2 is 1/4 A squared times R. So basically, it's going to be the same thing as 1/4 P. And then when we're looking at 1/4 P, we can actually see that the correct answer is going to be A, not B or C or D, right? Don't feel bad if you didn't get the right answer. As long as you can see how I did it and how it can make sense to you, the correct answer is going to be A, 1/4 P, and I use the calculation to get my answer correct, right? Someone says I must repeat that. Not a problem, Pulu, so I will repeat that for you. Let's have a quick look. So the first thing I wanted us to do is to say, how can we calculate power, right? Let's look at the values we've got. Can we use potential difference or voltage? Can we use current? Can we use, resistance? So one thing that we know is our resistance is the same because I said we're using identical resistors. So I know my resistance is going to be R. My current that I've got there. So when we look at this, current starts out of my battery down into resistor R1, then it gets to a parallel junction. At my parallel junction, it's going to split. Some of it will go to R2, some of it will go to R3, right? As that happens, let me just try and maybe erase some of these to make it a little bit less of a color fest, and then you can maybe have a look at what I'm talking about. So like I said before, if we look at this here, the current leaves there, it goes through R1, it gets to this junction. At that junction, my current is going to split, right? How does current split? Current splits to the ratio of my resistors, meaning the bigger resistor will get less current, the smaller resistor will get more, the bigger resistor will get less current, the smaller resistor will get, I keep confusing myself. The bigger resistor gets less current. The smaller resistor gets more current, right? Now, when it gets here, R2 and R3, which is bigger? No one is bigger than the other because they're both going to be equal, meaning my current will then also split equally. So then it'll split equally here and equally there. So whatever current I've got through R1, R2 and R3 will have exactly half of what R1 has. That's what I wrote this here. If I1 being the current through R1 is equal to A, then I2 being the current through R2 is going to be half of A. And then I3 being the current through R3 is going to be also half of A, because this plus that must give me this, right? The current through R3 and the current through R2 must give me the current through R1. So now I've got my resistance is equal to R. My current for R1 is A. My current for R2 is half A. Let me go plug that into my formula. So we know that power is equal to I squared R. And in this case here, we said the current through R1, we're going to call A. So then we know the power there is going to be A squared times R. Then let's do the same thing for R2. The power is equal to I squared R. The current through R2, we already said, is going to be half A, right? So we're going to say half A squared times R. So when we say half A squared times R, we need to square the half and square the A. That's how it works when I've got an exponent like that. Half squared is 1/4, A squared is A squared, and R stays as R. So if P is A squared R, that means this A squared R thing is also P. So I can replace it with a P, meaning the power for R2 is actually 1/4 P. And then we can see that the answer in this case is going to be A and not B or C or D. Hope that makes sense. You have time to redeem yourself. I'm going to give you another question that you can quickly try, right? So with this one I've got here, It says the EMF of a battery is E or epsilon, which is the actual symbol there. And its internal resistance is small letter R. The battery is connected to 3 resistors and 4 voltmeters, right? So we can see 1, 2, 3 resistors, 4 voltmeters. There's 1, there's 2, there's 3, and there's 4 voltmeters there. The resistance of the conducting wires is negligible, while the voltmeters have a very high resistance. Okay, got that? Which one of the following equations represents the reading on voltmeter V1? So let's quickly have a look. I'm going to just move this up a little bit so we can quickly see this together. It says which one of the voltmeter readings, one of the equations represents the voltmeter reading on voltmeter V1. So V1 is the one that's sitting connected across my battery. Then V2 is with R1, V3 is with R2, V4 is with R3. So their question is going to be A, are we saying V1 equals V2 plus V3? So V1, is it equal to V2 plus V3? Or is V1 equal to V2 plus half of V3? Or is V1 equal to V2 plus V3 plus V4? Or is V1 equal to V2 plus 2V3? There's the question. I'm going to give you guys 2 minutes to quickly try it. What do you think is the correct one? Simply write A, B, C, or D. Thanks, Tebogo. Thanks, Dumisho. Thanks, Puluso. Thank you guys for your answers. Thanks, Masego. Thanks, Rukhoto. Thanks, Lehonolo. And then the TikTok gang, whoever just joined our live, we've got a question up on the screen. Please make sure you guys go and you just give us the answer. So which one of the following is it? We're going to go through the question together, but it does always help if you guys take part. So put your answers in yourselves. Then when you're done, we're going to come back and look at it together, right? Which one correctly represents what we see on our screen? Thank you so much, Jabu, for your answer. Thanks, Kamohelo. You guys are doing really well. Thank you so much for your answers there. Okay, thanks, Dainty. I'm going to give everyone 30 more seconds, and then we can quickly have a look at which one is going to be the correct answer. Okay, for those that are on TikTok and joining us, please don't forget to like the live, share it with friends that you think they might benefit from, and make sure you follow us. We've got lots and lots of awesome videos. After the live, you can go back and check them out. We really would appreciate everything. But thank you guys all for the answers. I appreciate the interaction. It always makes the lesson so much better, right? Okay, we've got 10 seconds to go. Quickly put your answers if you haven't given us your answers, and then we can take it from there. 5, 4, 3, 2, and 1. Okay, let's have a quick look. Guys on TikTok, I've got A's. I've got C, I've got B, C, C, D, A. Let's go look at Zoom. I've got A's. Got a C there, A's, lots and lots of A's, a few D's. Okay, fantastic. So let's have a look at this thing again, right? And let's remember how this works. So remember, when we deal in series, our voltages are going to split. In parallel, our voltage is going to remain the same, right? So in this case here, when we look at V1, we look at it as follows, right? And V1, this R1 is in series with this parallel component, right? So with this parallel component, your V3 in this case is going to be equal to your V4. I'm going to take a moment, right, and just pause to explain why voltage in parallel is going to be the same, right? Just take a moment to explain why it's going to be the same. So if I zoom in here, remember what your potential difference is, right? It's the difference in electrical potential from one point to the other point. Now, when you measure potential difference, actually, you know what? I even forgot. I've got an awesome simulation that we can do together. So give me 2 seconds. Let me quickly get our sim up. Okay, Theo, just confirm if you can see my sim screen.
I can see it.
Okay, So I'm going to bring a voltmeter out that we can actually play with. So remember, guys, I try as much as possible in these science lessons to be able to bring out any kind of cool extra things that will help us learn a little bit better. So in this case, this is called PhET simulations, P-H-E-T. You can see there on the bottom right of my screen, right? And what PhET simulations helps us do is to really visualize some of these like science and chemistry based things that you might not be able to see physically when you're sitting at home. Cool. So in this case here, I've redrawn that diagram. So we've got this diagram here. Remember what we see? There's R1, and then you've got R2 and R3 in parallel. So when we quickly go back, we can see there on my left-hand side, I've got R1 showing, and then below that, so we can see here, I've got R1 on the left-hand side here, and then I'm going to have R2 over here, and I'm going to have R3 at the bottom over here. Now, let's have a look at what we're going to be doing. They said we want to look at V1 versus V2 and V3 and V4. V1, remember, was going to be the voltage across our battery. And then V2 was going to be the voltage on the left-hand side. V3 was the one on the top of the parallel, and then V4 was the one at the bottom. So let's quickly go measure V1. And I'm going to take my voltmeter, put it there at the bottom, and I'm going to put my terminals on either side of my battery, right? So when I put there, we get a reading of 9 volts, right? So I've got a reading of 9 volts there. Remember, write that down on a piece of paper. So our V1 in this case is 9 volts. Okay, let's go back and look at V2. So V2 is going to be this one. I'm going to put my terminals across V2, right? I've just put them the wrong way around. Let me just quickly fix them. So I've got V2 there, and my voltmeter reading on V2 is 6 volts. Remember to write that down. Let me actually do it as I talk to you guys, right? So we said V1, we got 9 volts there. V2, we got 6 volts. Let's quickly go back and try and measure any of the other ones. Sorry, I moved my image. Okay, now I'm going to measure V3. So V3 is here, and that's going to give me 3 volts. So I can quickly go write that down, right? That's 3 volts. Then I can also go measure V4 and then see what V4 gives me. Is the one just below there. Put my terminals there. And V4 also gives me 3 volts, right? So let me quickly go back. V4 also gives me 3 volts. So now when we look at it together, I can see there that V1 is 9 volts, V2 is 6 volts, V3 is 3 volts, V4 is 3 volts. So 9 volts is going to be 6 plus 3. So I'm either going to be looking at, so 6 plus 3, I need to be able to then go, what's that? Let's say V2 plus V3, that'll give me 9 volts, right? Another way to get 9 volts is going to be V2 plus V4, right? That'll also give me 9 volts. Right, now let's quickly go back and see V2 plus V3 or V2 plus V4. And then the one that I do have here is going to be A, right? V2 plus V3, the 6 plus 9. But how can I now, in your exam, you're not going to have this cool simulation that you can use. But this is going to really just show us that we can actually go and figure it out and work it out and see how it works. But how do we work it out without that simulation? So remember, the voltage, like I was mentioning earlier on, the 9 volts is what my battery can push out. The first resistor here uses a certain amount of that, right? When I get down to my parallel component, that is going to be using now something else completely, and then we're going to go back to my 9 volts. How much of that is going to be used? Remember, it's down to the resistance, it's down to the current, right? Where we need to go back and think about the fact that V is equal to I times R. So if the current through R1 is going to be, let's call that I, and the resistor R1 is going to be R, right? Then we know in this case here, the voltage V2 is going to be, so V2 is going to be I times R. But then when we get down to the next one, remember what's going to happen. What happens is that I have a case of my current splitting. So it splits across R2, it splits across R3, right? In this case, they didn't necessarily mention that they were identical. They don't even need to be identical, but we can kind of work out how they're going to be. But one thing that we do know is that the voltage across the two is going to be identical. So whether we say R2 times the current or R3 times the current, one thing that we know is that they're going to be identical V3 and V4. It's just how it is. We were looking at it earlier. When resistors are in parallel, the voltage across the two of them will be equal in that case there, right? And then that voltage is going to be the same voltage as if I were to put a voltmeter, let's say, for example, across here. If I put a voltmeter across here, measuring this point and this point, it will give me the exact same reading. It'll give me a reading of 3 volts as well. And if you want to quickly see and prove that that's going to be the case, let's have a look. So we measured V3, which was 3 volts. Let's go down to V4, that's 3 volts. But I even said to you, if I measure these points, the entire parallel circuit, notice I get the exact same 3 volts, right? So that's why you can see your voltage across a parallel circuit is going to become equal, because you're measuring the same potential before and after a parallel combination. So now that I know that that's going to be the case there, I can clearly see, okay, then whatever I get for V3 or V4, it'll be the same as I get for the entire parallel combination. And those two together should give me the same as my V1. So then you can clearly see that your answer there is going to be A. A lot of you got it correct, but I thought I'm going to spend some time really unpacking how we get to that particular answer. Thank you guys so much for your patience. We're going to get started with our longer questions just now. Remember to keep interacting. Remember to keep making sure that we go through this together. So I don't see any other questions. I'm going to jump straight along. We've got question 8, which looks as follows. So we've got a battery with unknown EMF, E or epsilon, and unknown internal resistance R, right? This battery is connected to 3 resistors. So we've got the resistor there, 3 ohm, 2 ohm, and 5 ohm. A high resistance voltmeter, 2 switches, and 2 ammeters shown below. So there's our question 8. Let's look at some of the questions they're going to ask us about question 8. 8.1, it says, state Ohm's law in words, right? Ohm's law in words really talks about the potential difference across a conductor is directly proportional to the current in the conductor at a constant temperature, right? Or you can say the ratio of the potential difference to current is constant at a constant temperature, or you can say the current in a conductor is directly proportional to the potential difference across the conductor at a constant temperature. As long as you make a reference, right, for Ohm's law to the proportionality, right, of V and I. If you can make reference to the proportionality of V and I in whichever way, then you will basically get those particular marks there. So let me just quickly put in the definition just so we can save time, so I don't have to write out the entire thing. I'm going to just paste it in there. Give me 2 seconds. Okay, so there's our definition there. One we can use. The current in a conductor is directly proportional to the potential difference across the conductor at a constant temperature, right? Provided all other physical conditions remain the same, essentially, is that constant part that we need to deal with. Now it says both switch S1 and S2 are closed. The reading on the ammeter A1 is 1.5 amps. So let's quickly look. S1 and S2 are closed, and the reading on the ammeter is 1.5 amps. What I like to do always is to ensure that I like to sort of code my current, right? So I'm going to code my current in here. So the current that goes through my battery, I'm going to code in green. I'm going to get to a parallel junction. It's going to split. It'll split to this red current. Sorry about that. It'll split to this red current. Let me use a highlighter actually. So it's going to become this. So it'll start off as green. So the current through here is going to start off as green. Okay, it'll get there, it's going to split up to this pink one, and then ammeter A1 is going to always give me the pink reading. Right, and then this is going to be pink again, it's going to go up to there, then it's going to rejoin, and then, for example, then the current through here is going to be this blue current. It's going to rejoin, it's going to be green current back, that's going to give me A2. So now I know that wherever I see green current, I'm dealing with A2. Wherever I see that pink or purple current, I'm dealing with A1. Okay, now let's quickly go back for this question. It says, give the reading on the voltmeter. Now the voltmeter is sitting there over the 3 ohm resistor. Now, here's the voltmeter we're dealing with. So again, voltmeter, I'm dealing with Ohm's law, V is equal to IR. I've got the resistance, but I don't know what that blue current is, right? So I don't have enough information to be able to deal with this. And then we've got a question there that says, does it have internal resistance? The question did say yes, it's got unknown internal resistance R, right? So they said find the reading on the voltmeter. Now again, we don't know what the blue current is, but one thing that we do know is that the voltmeter reading on this parallel branch is going to be equal to the voltmeter reading on that parallel branch, right? Because my voltage in parallel will be the same. And on my other parallel branch, I've got enough information because I know what my pink or purple current is. It's been given there as 1.5 amps. And I know my resistance in that branch. I've got a 2 ohm resistor and a 5 ohm resistor. I've got 7 ohms in that space. So I've got enough information there to work out the voltmeter reading or the voltage of that branch, because it'll be the equivalent to the same as the voltage reading of here. So let me use that second branch of A1 to work that out, right? So again, V is equal to IR. Let's quickly jump straight into that one. So V is equal to I times R. The current was given to me as at 1.5 amps. The resistance in that branch is going to be these two, the 2 ohms plus 5 ohms, right? And you take those 2 ohms plus 5 ohms, you can put them all together. That's, 2 plus 5. And then you put that into your calculator, you should get an answer of 10,5 volts, right? Thanks, Wakila, for dropping your answer really quickly. Really appreciate it. Bianca, thank you for your answer. 10.5 volts is correct. Well done, guys. Hope you guys did well there. So we know that 10,5 volts is going to be the reading on this voltmeter here. Okay. Awesome. Well done for you guys. Now it says, find the reading on ammeter A2. Let's quickly go back and have a look at that. So ammeter A2 is that green ammeter there, right? How can we find that? We don't have the V total just yet. We don't have the R total, although we can work it out. But there's an easier way, right, to do it. There's a question from Olotu saying, why don't you add 3 ohms? So Olotu, the reason why we don't add 3 ohms is because we were working on this branch. And the 3 ohm resistor is on another branch. So we're working on this branch here to find the voltage of that branch, because we know that it will be equal to the voltage on the blue branch. So on my purple branch, I only have 2 ohms and 5 ohms in that branch there. Hope that makes sense. To find ammeter A2, remember what I said, you're going to have your green current splitting into blue and purple. So how do I find the current are we dealing there? Because the question is asking for a reading on ammeter A2. A2 is this green current here. I need to just go and find what is my current through blue. If I add that to purple, I now know what my green current is. So let me quickly go and find my blue current, because I now have my voltmeter reading and I've got voltage. I can go work out what the blue current is, where I is equal to V over R. It's that simple, right? So to quickly do that, I can say I is equal to my potential difference over my resistance. What is my V? We just worked it out. It's going to be 10,5. My resistance now is where we can use the 3 ohms, right? As to Olotu's previous question. We can now use the 3 ohms because I'm dealing in the blue branch now, divided by 3. And then when you put that together of the 10.5, and then we divide that by 3, you should get an answer of whatever follows. You guys can quickly check that on your calculator and tell me what answer you guys get there. 3.5. Well done, guys. We're going to get 3.5. So then the current is going to be 3,5. But remember, this is not the reading of ammeter A2. It's only the current through that 3 ohm resistor, right? So I'm going to make a note here. This is going to be current of my 3 ohm resistor. I need to find the current for the entire thing. So that's going to then be I total. So my I total, or my current of A2, is going to be the current A1 plus the current A3. And then that's going to give me A2, right? Current A2, so it's going to be current of A1 plus the current of A3, which we worked out. And then again, the current of A1 was given to us already. That was given to us as 1.5 amps. We can see that over there. The other one of A2 or A3 we just worked out. So we can put that in there. And then we know we end up with 1,5 plus what we just worked out, 3,5. And then we know that the current on A2 is going to be a total of 5 amps as my final answer. Okay. Prudence says I forgot the units for the intermediate one, 100%. Don't forget those units there, 3,5 amps. As long as for my final answer, I've got the units there. It does work and it works quite well. So it's very, very important. So if Prudence, just as a note, for my intermediate calculations, I don't necessarily need units, but you definitely must have units for your final answer. That is a very important one in that case there. But yeah, it's good to keep the units everywhere, then you won't forget them. So thank you for that note there, Prudence. And then someone's asking to see the question for 8.2.1. It was asking for the reading on the voltmeter, the question 8.2.1. The reading on the voltmeter is the voltmeter there that sits on my blue branch in that case there. Okay, hope that's good. Let's quickly go down to 8.2.3, right? Now they want us to calculate the power that is dissipated in the 3 ohm resistor. Let's quickly go look at what's happening in my 3 ohm resistor. So my 3 ohm resistor, we worked out there. The resistance is 3 ohms as given. We found that the voltage across there was 10.5. We also just worked out that the current through there is 3.5. So we can use anything that we want to use essentially there, but I'm going to make sure that I want to use something with the resistance because that was given to me, right? So if you look at my various equations for power, we've got power is equal to I squared R. We've got power is equal to, let's quickly go back to those notes we were looking at. There's V squared over R is one of them as well. Where did I do power? There we go. There's V squared over R and there's also V times I. So I squared R, V squared over R, and V times I. And then as we do that, we can pick one that's going to work for us. So in red, we've got V squared over R. It's also going to be equal to I times V. Of those three equations, which is the better equation to use? What I would say for this question, not in general, for this question, I would avoid using I times V, right? Because I was given R, I calculated I calculated V. If I made a mistake in any one of those two, I have a better chance of getting it wrong. So I'm going to either use one of the first two ones in that case there. In this case, I'll just use I squared times R just for no apparent reason. But remember, you are allowed to use any of them. Any one of those three will work if you know you're confident with everything that you're dealing with. So I'm going to use I squared times R. The current we calculated in the 3 ohm resistor was 3,5 amps. That's going to give me, sorry, my pen was misbehaving there. 3,5 squared times the resistance is given as 3 ohms. You can plug that into your calculator to then solve for the power that's dissipated within here. And then you guys should get an answer. Masejo's got it there. Wakile's got it there. Thank you so much. Biente gave us a good answer there. Please remember your units, Biente, for power, right? Power is measured in watts, not joules. Joules is energy and work, but the units are correct. So it's going to be 36,75 watts. Very, very important. That's going to be the power dissipated in the 3 ohm resistor. Hope that makes sense to you guys. I'm going to move on to the next question. Remember, we're planning for prelims, right? So prelims can sometimes be a little bit tricky. The next question is going to be one of those. Remember in this session, I'm warming up. I'm warming us up. We're going there step by step. And then at the end of the day, we're going to come across, I don't call them difficult questions. I call them challenging questions. And when the questions get a bit challenging, you guys will rise up to the challenge. So let's go and let's rise up to the challenge of the very next question, right? So let's have a look at this and see how we can work it out. The questions reads as follows. Switch S1 is now opened while switch S2 remains closed, right? The reading on the ammeter A2 is now 3.64 amps, right? Calculate the EMF of the battery. there's a question we need to now try and work out. So switch S1 is now open while switch S2 remains closed. The reading on the ammeter A2 is now 3.64 amps. So I need to quickly go back and then re-change and look at this image and how it's going to work. So I'm going to remove all of this stuff here because everything's going to now change. So if I remove all of these here, we can now look at the changes. So the question that we're dealing with here tells us the following information, right? So the switches are going to now move about and things are going to change a little bit. So switch S1 is now open. So let me quickly try and annotate here what an open switch is going to look like. We try and add, there we go, do there. So I'm going to open up switch S1. Let me quickly do this. Okay, so we can see switch S1 now. We've opened that one right up. So this is an open switch, okay? And now it says, while switch S2 remains closed, okay? Then it says the reading on ammeter A2 is now 3.64. Then we know this reading now is going to be 3.64 amps. So that's the change that's going to happen right now, okay? Here's a quick question before we go too far. When I open switch S1, what will the reading be on ammeter A1? I want you guys to post the answers in your chat. If I open switch S1, what will happen to the reading on ammeter A1? Quickly post that. I'll give you a minute to think about it. If I open switch S1, what happens to the reading on ammeter A1? Sana gave us an answer there on Zoom. Thank you so much. Okay, to the guys on TikTok, if I open switch S1, what happens to ammeter reading? The ammeter A1, what happens to that reading? Thanks, Mitumelo, for your answer as well. Thanks, Pamzile, for an answer. Okay. So very, very important, right? And then I'm getting some good answers there. There'll be no flow of current through that branch, right? Meaning A1 is not going to have current flowing through it. A1 is going to go right the way down to 0, right? So A1 is going to now go all the way. This is going to fall away. I'm going to now basically have 0 amps through A1 because no current's going to flow. All I'm going to have is current flowing just up here. So current's going to flow like this, down here, this way, up, and through there. That's what my new current flow is going to look like. I'll have no current flow at the bottom of my circuit. Good eye for you guys picking that up, right? Now, they want us with that to calculate the EMF of the battery. Now, how are we going to go about trying to calculate the EMF of our battery, right? Because at this point, we've got the particular equation. So EMF is going to be EMF is equal to capital I, let me quickly fix that, times capital R plus small letter r like that. So if we're looking at this, yes, we do have the capital I, we do have the capital R, but we don't have the internal resistance. So then we've got two unknowns, right? And when I've got two unknowns there, that becomes a little bit of a problem for myself. But I know that to calculate EMF, I need to use this equation at some point, right? Someone did ask that question on TikTok, are we going to use that equation? 100%. We're going to use that equation. But now we've got a problem. I've got two unknowns. Now, I want you guys to tell me, what do I need to do when I sit with a scenario where I've got two unknowns? What do I need to do? I'm going to give you guys 15 seconds to think about that. What do you do when you have two unknowns? What do you do to solve for things if I've got two unknowns? Okay, I've got some great answers there from our Zoom community saying we need to solve it simultaneously. There we go. Even Pamzila there and Olweto on TikTok said we're going to solve it simultaneously. So now how do I get my second equation, right? So now I need to figure out, I need two equations to be able to solve this thing, which on my side is not going to be bad because I've been given two scenarios. I've got the scenario where my switches are all closed. That is one scenario. I will use that equation. Then I've got the scenario where my one switch is going to be opened and I've got new information. So now I can use that information for both of those For that one reaction, write it 2 ways and then solve it simultaneously. Okay, I'm glad you guys are ready and you guys knew we were going into this direction. Remember, it's not a difficult question. It's only a slightly challenging one. And we're going to nail it because you guys are on the ball today. All right, let's go. Let's quickly go back and then look. So let's first start with the information that's been given to us right now and then use that as our sort of step 1. So let's quickly write that equation down. We've got EMF is equal to I into capital R plus lowercase r. Let's substitute what we do know, right, about this. So in this case here, for the equation as it stands, let's call that equation 1. My resistance is going to simply just consist of this over here, the 3 ohms, and my current is going to be this 3.64. That's going to be my current. That's my resistance. I don't know what my internal resistance is. I don't know what my EMF is going to be, but those are going to be consistent across the two. So let's quickly go plug that in for this particular question. So for my equation 1, I'm going to substitute those values there. I've got EMF is equal to my current was given as 3.64. My total resistance is going to be 3, and my internal resistance is going to be R. I'm going to call that equation 1. For my equation 2, I'm going to use now a different version of this equation. I'm going to use the version that I got from the very, very beginning. So that's going to be my equation 1. Equation 2, I'm going to use the beginning part of this question. So before any of the switches were opened, right, that's going to be my equation 2. So for equation 2, I'm going to say, well, EMF is going to remain as E. My current through ammeter A2, we did work it out because the question did ask us the reading on ammeter A2, and we worked out that that was going to be 5 amps, right? So we worked that out to be 5 amps. So that'll be the current for equation 2. Let's substitute that one in. That's 5 amps times capital R. So when all my switches were closed, right, I have parallel resistance. I'm going to have 3 and 7, the 2 plus 5. I need to work out what my R total is for when all my switches are closed. Let me quickly do that on the side here, right? For equation 2, I need to quickly work out what my R total is. Remember, 1 over R total is equal to 1 over R1 plus 1 over R2. R1 and R2 being whatever's going to be on my 2 branches, right? Tabani is asking what grade. We're doing grade 12 electric circuits. So let's quickly work this one out. So before my switches were opened, I had 3 ohms on one, 7 ohms on the other one, because it's 3 ohms and then 2 plus 5 will give me 7. So then I'm going to have 1 over 3 plus 1 over 7. That is going to give me 1 over R total. Now I can quickly put that 1 over 3 plus 1 over 7. If you put that in your calculator, quickly tell me what you guys get. 1 over 3 plus 1 over 7. What do you guys get in that case there? Oh, you guys are quick. You guys went straight to the final answer. I appreciate it, right? So 1 over RT. I'll do the intermediate step for those that are just following that way. 1 over 3 plus 1 over 7 is going to give me 10 over 21. Therefore, my R total or my R parallel in this case is going to give me 2.1 ohms. So that's going to be very important for me to work out my R total. That 2.1 ohms is going to then go in here, 2.1 plus my internal resistance R. And this is going to be my equation 2. Now I've got 2 equations, equation 1 and equation 2. All I need to do is solve them simultaneously to find what my value of EMF is going to be. So you got 2 choices. You can either solve for R, substitute back and get E, or you can solve for E directly by making everything equivalent to R. I'm going to just do it the way that's easier because I've already got them in terms of E. I'm going to first say, well, equation 1 is equal to equation 2, find R, substitute R back, and then work it out that way. But whichever way you like to do simultaneous equations, do it that way. And that's the way that will basically work for you. So I'm going to then say, well, in this case here, we have E there and E there. So I know that 3 comma 64 into 3 plus r must equal, for what we had in equation 2, 5 into 2 comma 1 plus r. That way there. Let's quickly go and work this one out. Right, 3 comma 6r. So what I'm doing here, basically saying my equation 1 equal to my equation 2. So in there, we can then say 3 comma 464 times 3, which is going to give us 3 comma 64 times 3 is going to be 10 comma 92. You just move that to the side. Plus 3,64 times r is going to give me 3,64 r. That's going to be equal to, on the other side, 5 times 2,1 is going to give us 10,5. Right? 5 times 2,1, that is 10,5. Plus 5r. And then when I solve for r in this case here, I'm going to try and be very quick with it. You can see 5r, I'm going to minus 3.64. So we're going to have 5 minus 3.64 equals 1.63. So I'm going to have 1.36r in that case there. And then 10,92 minus 10,5 is going to give me 0.42. And then with r, I'm going to say 0.42 minus, divided by 1.36, right? 0.42 divided by 1.36 is going to give me an r of around 0.3, right? 0.31. That's what I get for my internal resistance, right? 0.31. Thank you guys for those who've been putting the answers in there. Well done. Now I need to go find what my EMF is, and I can substitute that back into equation 1 or equation 2, completely up to you. I'm going to put it into equation 2, right? So into equation 2. So into equation 2 says my EMF is equal to 5 into 2,1 plus r. So I want you guys to quickly then substitute that, knowing that r is 0.31, substitute that and find our value for EMF. Let's see how we go. That'll be 5 into 2,1 plus 0.31. And then in that case there, you should get an answer of, let me see, 0.31 plus 2,1 times 5, and you should get 12,05 volts. Okay. Thank you so much. I see people are getting some great answers there on TikTok. Thanks, Bentley. And thanks for everyone who's posting there. And then even on Zoom, Vikanyo, Ayanda, Precious, Wakile, thank you guys so much. If I didn't mention your name, but I appreciate you for posting the answers, right? The question wasn't too bad. It wasn't too hectic. It was just a little bit challenging, right? All we had to do is just take ourselves step by step. And what I'll do is I'll quickly repeat the steps we had to do to solve for this answer. So the question said, switch S1 is now opened, while switch S2 remains closed. Let's quickly go back and look there. So S1 is opened, we can see down there, here, and then S2 remains closed. Now they said, find the EMF. Now we know we have to use the equation for EMF, which looks as follows, right? But when looking at it, we have current and we've got the resistance, but we don't have internal resistance and we don't have EMF. We have two unknowns, which you guys then so correctly then identified that we need to go back and then solve them simultaneously. But how do we then solve it simultaneously when I only have one equation? I need to develop two equations by looking at two scenarios of the same equation. Scenario 1 is when all of my switches are closed. And then that gives me an equation. Scenario 2 is when my switches are open. That gives me one version of the equation. And then we can clearly see here, what I did is then equation 1, I used the open switch version. Equation 2, over there, we've got the closed switch. Once we figured that we filled those values in, all we did was mathematics beyond that point, and we solved it simultaneously. Fantastic there. Bianca says she's enjoying now. I'm glad that you're enjoying it, right? Even though it's challenging, it's still very doable, right? And I think you guys are going to do really well come prelims, guys. Really, really appreciate it. Anyone who's just joined us on TikTok, we're going through some electric circuits questions for grade 12. We're about to go to our next question, so you came right on time. Fantastic. And then finally, to wrap this particular question up here, we've got switch S2 is now opened while switch S1 is closed. How does the voltmeter reading change in this case, right? So let's quickly go back and look at what happens. So they said switch S2 is opened while switch S1 is closed. So let's quickly go back to the beginning. And then what happens here, let me do it in purple. So they now open up switch S2, and they close up switch S1. And the question then asks us, while this is happening, right, how does the voltmeter reading change, right? So we've got a voltmeter that's going to be right here. How does that voltmeter reading change when we open switch S2 but close switch S1? How will that voltmeter reading change? Choose from increases, decreases, or remains the same. So I want you guys to post in the chat. After what happened, we close switch S1, we open up switch S2. How will it change my voltmeter reading? Right, increases, decreases, or remains the same? I'll give you guys 2 minutes to have a quick think about it, right? All right, I see some answers are coming in. We've got some stays the same, some decrease, an increase there. Zoom side remains the same. There's some increase, some decrease. So there's a wide variety of answers. I'll give you guys 15 more seconds to quickly have a think. Those of you who haven't sent your answers, quickly send your answers in. Even if you guess, it's fine. Send your guess. We'll correct each other just now. 10 seconds to go. Okay, let's quickly have a look at how that would change, right? Sorry, is my mic on? Yes, my mic is on. Let's have a look at how that would change our system. So in this case here, so I want us to have a look at a few things. Whenever you get a question of this switch is open, that switch is closed, you need to think in this following order. Number one, how is my resistance changing, right? How's my resistance changing? And how will that change in resistance affect my current? And how will that current change affect my my resistance? And sometimes also you need to consider, because in this case we've got internal resistance, how will that current affect my internal resistance? How does it affect my voltage overall? So the first thing we can see is, what is this voltmeter measuring in case one, where we've got S1 open, S2 closed, where we've only got the green current flowing? So this is going to be measuring my V external, right? It's going to be measuring V external, the total voltage coming out of my battery, right? The energy per unit charge, per coulomb coming out of my battery. And then if I then close S1 and open S2, this is still going to be measuring my V external, right? Just that now I'm going to be dealing with a slightly different resistor selection. So let's have a quick look. So when we look at this, my resistance initially was 3 ohms. But when I open S2 and I close S1, what happens? I change from 3 ohms to 2 and 5. That becomes 7 ohms. So the first thing that happens there is my resistance increases. I hope everyone notices that, okay? If you're with me so far, put a thumbs up as your reaction or thumbs up in the chat so that I know you guys are with me. I'll quickly repeat that. When I open switch S2 and I close switch S1, I take my circuit from this top part, but if I open switch S2, my circuit now becomes this part here. So from the green circuit, I now basically have, let me draw a different color. I now basically have a blue circuit that does this. So I go from the green circuit at the top to the wider blue circuit. That's what happens when I change my switches, which means my resistance used to be 3 ohms, but now in the blue circuit, my resistance is going to be the 2 and the 5 ohm. I'm going to get 7 ohms in total. So my resistance increases. Okay, hope that makes sense to everyone. Thank you for the thumbs up on TikTok there, and I think everyone's on board with me. Now, when resistance goes up, what happens to current? Right? Remember, when my resistance increases, what does resistance do? It opposes the flow of charge. It really slows down. It works against my current. So when my resistance goes up, my current goes down. Very important. When my resistance goes up, my current goes down. Now, if my current goes down, what's going to happen? Even the current through my battery, very important, even the current that goes through my battery there, even that is going to decrease, right? And when the current through my battery decreases, my V lost, my lost volts are going to decrease, right? So when my lost volts decrease, EMF is consistent. That means my V external is going to decrease. If I've got less losses in my battery, I've got more, EMF or potential difference or energy per unit coulomb to go out of my battery. Then my V external increases. And like we mentioned already before, what are we really looking at? This V is measuring my V external. And when they say, what will happen to the voltmeter reading? The question is asking, what happens to my V external? And remember, again, very important, when you look at this EMF equation, right? We have I into R plus R. And what does that give you? I into R plus R gives you the following. It means I into capital R is going to be V external. Let me actually write it out a little bit more. I capital R plus I small letter r. And what does that give us? I capital R gives me V external. It's the voltage that I have accessible to use across my entire circuit. And then I small letter r is going to be my V lost, right? My V internal. It's the lost volts inside the battery, right? It's my cost of doing work. It's the cost of what the battery needs to do internally. So to figure out what happens to my V external, remember, EMF remains constant. I need to go and look at that system there. What happens to my resistance? How does that affect my current? How does that affect my voltage? And the first thing is the current through my battery goes down. That means even my V lost will go down. And if V lost goes down, the rest of that electrical energy goes outwards into my V external. And then we know that our final answer means that the V external there will increase. So the voltmeter reading, here's your final answer, will increase. And then the next question says, explain what that happens. And we just did that explanation. The 4 steps is my total resistance goes up. The current in my circuit goes down. When the current in my circuit goes down, my V lost goes down. And therefore my V external will go up. Cass says I need to please repeat V lost, and I'll do that with pleasure, Cass. What V lost is, remember, when we are dealing with a battery with internal resistance, right? There's a little bit of resistance inside. It's the energy that I use inside my battery to move that current along in the battery. So when we are dealing with this, remember there's the equation EMF is equal to I into capital R plus small letter r. When I multiply this out, I capital R is there, I small r is here. What do each of those things tell me? I capital R is V external, right? That is what my voltmeter reading is going to give me if I've got any kind of voltmeter around my cell or my battery, right? That voltmeter, when everything is closed, is going to give me a reading of V external, right? Now, V external is dependent on how many lost volts or what voltage do I lose inside my battery. The more voltage I lose in my battery, the less my V external is going to be. The less I lose in my battery, the more my V external is going to be. So in this case here, I increased my resistance from 3 to 7, right? Which means the current in my entire circuit went down, which means when the current goes down, remember, it includes the current that goes right through my battery, right? And that current through the battery, sorry about that, that current through the battery goes through, you can imagine this internal resistor, and that IR is going to go down. And when IR goes down, it can't just go to nowhere. It's got to go somewhere because EMF is constant. So I can't lose it out to the system. So if I lose it in the IR, it's got to go to my I capital R. So my V external has got to increase because EMF is equal to V external plus V lost, or you can say V external plus V internal. So that's basically how that whole thing there works. Cool. We've gone through that particular question. I'll pause for any questions anyone has got right now. And then I've got another question for us to do as well in the last 30 minutes of this session. But let me first pause for any questions before I move on to ensure that you guys have good clarity on what we've just covered. I'll give you guys 2 minutes to have a think about it. For those that have just joined us on TikTok, thank you guys so much for joining us. Please don't forget to follow us. We do appreciate all the follows. Share the live so that your friends can also come and join us. And make sure you go and watch all our other awesome content. So the guys on Zoom and on TikTok, we've got a lot of awesome content on our YouTube. If you've missed our previous lessons, go to YouTube. We're posting them all on YouTube there. And then you can catch our previous lessons to catch up. But remember, watch live. Watching live is always the best way. Because when you watch live, you get to ask questions. We get to really repeat and do everything with you, right? Cool. Dumisha says, please repeat it again. So Dumisha, I've gone through it about twice at the moment. I recommend by tomorrow, this should be up on YouTube. Go and watch it on YouTube. Watch me do it step by step, right? And then try and make the notes yourself at the same time so that I'm not going and repeating the same thing over and over again. And then if it still doesn't make sense there, do me sure if you're at one of our schools that we support, go chat to your tutor and then ask them to just sort of sit down and give you a session about it and make them take you through the video. But definitely go rewatch the video. It should make sense. In a nutshell, when we close S1, open S2, we're changing from that green circuit, this one here, to the blue, the wider circuit, this one there, which means my resistance is going to change from 3 ohms to 7 ohms, the 2 plus 5. So when my resistance increases, my total current in the circuit decreases. When that decreases, right, if I goes down, it means V lost goes down. When V lost goes down, my V external will then increase. And therefore, if V external increases, the voltmeter reading, that one there, will then increase. Cool. Dumisha, I hope that helped you guys a little bit. Bianca says there's no class tomorrow. So Bianca, please remember. So remember, usually we don't have classes on a Friday, usually. But we had technical issues on Monday this week. So we postponed Monday's lesson to tomorrow. So tomorrow there is a lesson. We're having a calculus lesson tomorrow. So yes, only for tomorrow there's going to be a lesson. Usually we don't do lessons on Fridays. So please do join us tomorrow for our calculus live. It's very, very, very important. Okay, let's jump into the next question, guys. Let me quickly go to it. Give me 2 seconds. We answered 8.4 on the diagram above there. Let's start with the next question here, question 8. Let's have a quick look at this diagram. Let's look at how all of these things look, and then we can begin to answer the questions, right? Okay, so the question there states that the circuit diagram below shows 4 resistors connected to a battery of EMF E or epsilon and internal resistance R, the lowercase r. The resistances of the ammeter and the connecting wires are negligible, while the voltmeters have a very high resistance, right? So assume no current flows through the voltmeters, and you can assume that current flows through ammeters and the wires without any disruption. Then 8.1, state Ohm's law in words. We did that in the previous question. I'm literally going to just copy and paste that question there, but you can see, guys, that this happens, literally like quite often, right? They'll ask these questions, they'll repeat these questions a number of times. So make sure you guys do note that, and that you guys actually put your definitions down and memorize them. These are 2 marks that you get here, 2 marks you get there, right? Cass is asking what time is our live tomorrow. Our live tomorrow is going to be 6 p.m. So usually we do our lives Mondays to Thursdays from 6 p.m. to 8 p.m. Mondays and Wednesdays, we cover mathematics with our great math tutor Tsapang. And then Tuesdays and Thursdays, we do physical science. So please make sure you join us for those. Cool. Now they said to us in this scenario here, before I go too far, I'm going to quickly go and do the thing I like to do previously where I annotate and look at which current flows where, right? So let's do the blue current. So we're going to have current coming out there. This is the ammeter reading. I get a parallel junction. So I'm going to split. It's going to split that blue current into, let's say, green current. That's going to flow like this until it rejoins this parallel junction. And then it splits maybe between green and this sort of pinky purple color. When they join back again, they become blue once more, and they'll go right through the battery back there to the beginning. Right, to make them a little bit bigger so we can actually see them. This is what happens there. Then we also had a green one, and that pinky purple color as well. So hopefully those colors are visible. So why I like doing this, it's because it shows me that whenever I look at any value there, so if I see that 3.5, it's in blue, anywhere I see blue, the current there is going to be 3.5. Where I see a different color, right? I see the pink, the 1 ohm, anything there's going to be that particular current. In green, I'll have a different value of current so that I don't go and repeat and reuse those ones there. Someone's asking, what are the important definitions in this topic? We went through them at the beginning of the session. As I mentioned, the session will be recorded. You can go to our YouTube and watch the session. After the fact, it should be live and up by about tomorrow. Awesome. Okay, so now they said S is now closed. That switch is closed. Awesome. The reading on the ammeter is 3.5 amps. It's noted there, the blue current. Calculate the total external resistance of the circuit. That's cool. So we can see we've got a parallel junction, right? Here's my parallel junction with 2 branches. Branch 1 with 1 ohm. Branch 2 is the green branch, right? And then I've got the 4 ohm in blue that's in series. So I need to first work out my R parallel, add the series one, and then I can put that all together. Let's quickly go do that. R parallel first, and then I can work out my series. So in this case here, 1 over R parallel is equal to 1 over R1 plus 1 over R2. And then in that case, there 1 over R parallel is equal to, so R1, I can use the 1 ohm in the pink, and then R2, I'm going to use the 3 plus the 2, right? So I'm going to have, sorry, quickly go back, that's 1. It's going to be 1 over 1 plus 1 over, and it's going to be 3 and 2. 3 plus 2, and then I need to basically work out what is going to be RP. You can then easily take those 2 there, put them in your calculator, or you can do them step by step, completely up to you, right? When you're able to work with these kinds of questions. So in 8.2, what we're looking for there is 1 over RP. When I put it all together, I should get 1 over 5 plus 1 over 1. That's 5 over 5 plus 1 over 5, which will give me 6 over 5. So it's going to be 1 over RP is equal to 6 over 5, which means my R parallel is going to be 5 over 6. If you look at that in terms of, in proper numbers, it's going to be 0.83 ohms, right? Thank you so much for the ones who've posted the answers there. Now I need to do my R total, which means I'm going to just add that to my R series. So my R total equals my R that's in series plus my R that's in parallel. My R in series, if I go back, it's that 4 ohm resistor. That's going to be 4 plus my R parallel is 0.83. And then my R in total is going to be 4.83. Units are very important, ohms, right? Make sure you guys got that and it makes sense. Thank you so much, Kitumetse and Kimberly and Sane, for giving us that great answer there. And Anduso on TikTok, well done, guys, and Bianca as well for giving us that answer. That's now my total external resistance in the circuit. 8.2.2, calculate the reading on voltmeter V1. Let's quickly go back. The reading on voltmeter V1, I need to then look at what is voltmeter V1. Voltmeter V1 is this over here, and that's going to be giving me a value of whatever my V external is going to be, right? That's going to be my V external because my switches are all closed and I do have energy flowing in my circuit. And in that case there, I can just use V external. I can say I times R, as long as I've got the current flowing through the battery, which I do, it's that 3.5 that was given to me. And I've got my total resistance, which has already been calculated in the previous question. I can work out my V external. Nice and easy, nothing too hectic, right? Let's quickly go do that. So to work out my V external, V is equal to I times R. What is my I? My I is the current that was given to me, right? And that current is going to be 3.5 amps. My resistance, I just worked that out. And that resistance in that case is going to be 4.83. If I plug that into my calculator, you guys should come out with an answer of 16.91. Well done there to everyone who's answered. Well done, Biantle, Andiswa. You guys have got some good answers there. Thanks, Kim and Kitumets and Sunny for the answers as well there on Zoom. Really appreciate your guys' interaction in this session. Okay. There, 8.2.2, nice and easy, nothing too hectic for us to handle, right? So when we are doing this, let's jump to 8.2.3. It says, how does the reading on voltmeter V2 compare to the reading on voltmeter V1? Choose smaller than, equal to, or greater than. Let's quickly look at this. We're going to compare V2 to V1. Where's V2? V2 is going to be this one here. Hi, Theo.
They say you left units there.
Thank you
that answer.
very much. I did. Thank you. Volts, 16.91 volts. Really appreciate it. 8.2.3. How does V2 compare to V1? So we can see V2 is going to be this voltmeter over here. Looking at the parallel component, V1 is going to be my V external. I want you guys to post the answer in the chat. How does V2 compare to V1? Write smaller than, bigger than, or equal to. Thanks, Sanya, for your speedy answer. Let's see if anyone in the TikTok community can give us there. How does V2 compare to V1? Is it smaller than, is it greater than, or is it equal to? Thanks, Deboho, for your answer as well. Appreciate it. We've got two answers saying that. Andy gave us an answer of equal to as well. Ben is giving us an answer of greater than. So again, let's have a quick look at how this is going to work. Thank you, Brilliant, for your answer. So in this case here, right, when we're dealing with V external versus what's going down here, V2 is going to be smaller than V1, right? V2 has to be smaller than V1. They didn't ask for a reason, but let's go through the reason so that we can actually understand why. Remember that V1 measures everything that's going to come out of my battery, right? That's going to always be the biggest possible value. Your V external, the only thing that will be bigger than V external is going to be EMF. So EMF is going to be the biggest number. V external will be the next biggest number. Anything else in my circuit should be smaller than V external because the V2 plus whatever's going to be over, let's say I were to put a voltmeter here and call that V3 over my 4 ohm. So basically V1 is equal to V3 plus V2. So V2 has to be smaller than V1. That's the reason behind what I'm dealing with there, because the sum of my voltages across the circuit must add up to my V external. And remember with that, you treat your parallel circuit as one component in your circuit when you add up the voltages. Don't add up the voltage for each individual component in a parallel component combination. The parallel combination overall is one thing, plus anything else in series that must add up to V external. Therefore, V2 is a component of V external. It has to be smaller than V external in that particular case. It cannot be bigger. At best, it can be equal to, but in this case, it will be smaller. Okay, awesome, guys. So someone says there, on the 5 resistance, total current doesn't go through. I don't see where there's a resistor with 5 ohms. Maybe I'm not quite understanding your question. If you can maybe rephrase it, I'll try and reanalyze it. But I don't see if there's another resistor with a 5 ohm, unless you're talking about the 3 plus the 2, right, as the 5 ohms, but you still have current going through there because my circuit, my switches are all closed. So current will go through there because current can't go through my voltmeter. That's why they always say you'll have voltmeters with very high resistance. That's why they state this here. No current is going to go through a voltmeter. It's not the same thing as putting a wire of negligible resistance. That's a thing to note. Okay. Let's quickly go down here. So the answer we had here was smaller than. I'm going to just underline it instead of rewriting it. This is our correct answer, smaller than. Okay, 8.3. A learner concludes, right, that the EMF of the battery is equal to the reading on voltmeter V1. So they're saying that the EMF of the battery is equal to voltmeter V1, right? Then the question is going to ask us about that. Define the term EMF. So again, define the term EMF. EMF is simply going to be our maximum work done by the battery per unit charge, or the maximum energy supplied by the battery per unit charge. Hi, Theo.
Boitumelo says, can you please repeat the smaller than one?
Okay, I'll do that just now. Let me finish with this question and I'll definitely do that. Okay, so quickly with the definition of EMF. EMF is our maximum energy or maximum work done by the battery per unit charge. So quickly going back with the smaller than, remember, when we were doing, let me go back to our original notes that we started off with. So let's look at a scenario like this, right? In a series circuit, right? The sum of the potential differences of anything in your circuit has to add up to whatever potential difference you're going to have across the entire thing. So if, let's say, this is going to be our V external, because this is connected to a battery, this is going to be the same as our V external. None of these can be bigger than this amount up here. They can't be, because this amount has to add up to this plus that. So if I've got 4 plus 8 plus 20 giving us 32 volts, I can't have any of those being bigger than their own sum. And your V external is the sum of all the voltages, right? So going back down to the question, not this one. Going back down to this question, V external is the sum of the voltages across my battery. So it's going to be the sum of V2 and V3. So V2 can't be bigger than V external because V external is V2 plus V3. So that's very important why it can't be bigger than. So automatically it'll be smaller than. Anything in my circuit can at most be equal to, but it'll never be bigger than. In this case, it's going to be smaller than because I have to also add V3 to get to V external. I hope that makes sense. And then let's quickly go through to the next question. Just looking at 15 minutes left, and I want to leave some time for questions at the end, right? Sorry about that. Cool. 8.3.2, is the learner's conclusion correct? Choose from yes or no. And it says the learner concludes that the EMF of the battery is equal to the reading on voltmeter V1. Is the learner's conclusion correct? Do you guys think yes or no? Quickly post in the chat. The learner says that the EMF of the battery is equal to the reading on V1. So V1 is what we're going to see on that voltmeter. Is that going to be the same thing as the EMF? Quickly post in the chat. Thank you, Sane. Thanks, Nene, on TikTok. Thank you. I appreciate you guys. Okay, there we go. Thanks, Rafila, for your answers. Thanks, Wakila. Thanks, Bitumelo. You guys are awesome there on Zoom. Right? That's not correct. You guys are right. You guys are right in that case there, right? That's not going to be correct. That's not going to be a correct conclusion. Give a reason for the answer to 8.3.2. And the reason there is that the battery has internal resistance. So you're not going to get EMF coming all the way out. Some of it is going to get stuck in the battery or lost in the battery as our lost volts, right? Someone said the heat energy is lost when I'm assuming you're trying to say when the circuit is on or the circuit is closed. Well done, right? The battery has internal resistance. Resistance, right? Which means we're going to end up with V lost at some point, because remember, V lost is I times small letter r. But because of the fact that the battery has internal resistance, the EMF is not equal to that voltmeter reading. Okay, well done to you guys there for catching that one there. Then they say switch S is now removed and replaced by voltmeter V2. So remember before, we used to have a switch over here. The switch is removed and replaced by a voltmeter, as shown in the circuit diagram below. How will each of the following change? Choose from increase, decrease, or remains the same. Then it says the power dissipated by the 4 ohm resistor. Before we go there, I'm going to take a quick second to show how that now affects. If I had a switch where V2 was, and now I'm placing V2, remember, voltmeters have got very high resistance, right? Very high resistance means that I'm going to have little to no current going through. In the case of this question, I assume no current goes through my voltmeter, which means now when I look at my battery, the current's going to flow in this particular manner here. It's going to go around there. It's going to be this pink current. It's not going to split down because it can't go through my voltmeter. It's going to skip right past there. It's going to keep going down through the 3 ohm, through the 2 ohm. It can't turn left because it can't go through that voltmeter. It's going to keep going straight past there, up, and then that's what we have. So essentially, we've now converted what we have there to a series circuit. Okay, now the question is going to ask, how will each of the following change? How will the power dissipated by the 4 ohm resistor change? Say decrease, increase, or remains the same. Quickly post in the chat. How will that change? Will the power dissipated by the 4 ohm resistor increase, decrease, or stay the same? Quickly put that in your chat. What do you guys think is going to be the answer? Thanks, Sunny, for your answer there. Thank you, brilliant. Thanks, Debuho. There we go. Answers are rolling in now. Really appreciate you guys. Okay, I'll give 10 more seconds for those that haven't answered. Quickly think about it. How will the power dissipated by the 4 ohm resistor change? Remember when I ask you these questions, whenever my circuit changes and shifts around, ask yourself the following questions. How does my resistance change? How does that affect my current? How does that affect my voltage? How does that affect power overall? So the correct answer in this case here is that it's going to decrease, right? For 8.4.1, it's going to decrease. Why does it decrease? When I now remove the switch and put V2 there, I've cut out my parallel resistance, right? When I remove my parallel resistance, what happens to my total resistance in my circuit, right? My total resistance goes up in my circuit. When total resistance goes up, my total current in the circuit comes down. And if current comes down, my power will come down because power is I squared R. The question didn't ask for an explanation, but I'm just giving it to you so that you guys are able to understand why that happens. Let's quickly, I'm going to write the reasoning just on the side there. When I remove that parallel junction, right, my R total will increase. When that happens, my I total will decrease. When I total decreases, the power of that 4 ohm resistor will decrease as well because power is I squared R. And if I goes down, then P goes down. So the correct answer for 8.4.1 is decrease. Give yourselves a round of applause if you got that one correct. Don't feel bad if you didn't get it correct. There's another question that you can try now. It says, and this is going to be not trickier, but I believe you guys can then do it. 8.4.2. How does the reading on voltmeter V1 change? Does it increase, decrease, or stay the same? Remember, this is our V external. We had a similar question on the previous one where we need to consider how V external changes. Follow the same path. Don't forget about those sneaky lost volts. The lost volt is the key to answering this question when it asks you how V external changes, right? Go for it there. So 8.4.2, how does the reading on voltmeter V1 change when I replace the switch with V2? Quickly go for it. Write down increase, decrease, or remains the same. Don't forget on TikTok as well, post your answers in the chat. Interactive sessions are lessons where you really learn a lot more. So the more you engage, the more you're going to learn in this session. Thanks, brilliant, for your answer. Thanks to Maho, thank you for Gitumetse. Really appreciate the answers you guys are giving there. I'm going to give everyone 5 more minutes. Thank you, Judith, there on TikTok for answering. Really appreciate it. Okay, I'm going to give you guys are almost there. Thanks, Rotabile, for your answer. Let's go. Thanks, Moses. Thanks, Bucanio. Let's quickly go. 5, 4, 3, 2, 1. Okay, so the correct answer, drum roll, please, is going to be for 8.4.2 increase, right? The reading on voltmeter V1 is going to increase. Why does that happen? Let's look at the reasoning, right? So remember, the same reasoning is going to follow. Let's look at how things began in the beginning. When I remove parallel resistors, my R total does what? It goes up, right? How does that affect my current? My current, my I total goes down. And I told you guys, think about those pesky little lost volts. How does I total going down affect my lost volts? It means my V lost goes down, meaning my V external goes up. And there's our answer to tell us that that is going to basically increase in the same way that the previous one, the power decreased. It's the same kind of methodology. It's important to be able to know how to go through these questions in this methodology, right? And a lot of these, if you can answer 8.4.1, 8.4.2, a lot of the multiple choice questions that you get for electric circuits come in this fashion. So if you guys can answer these questions, you're doing really well and you're on your way to nail these prelims that are coming up, and then you'll do very well for your guys' finals. I believe in you. Okay, let's quickly do the last question and wrap up our session for today in the last 5 minutes. It says, explain the answer to question 8.4.2. We actually already done that, right? But I'll quickly repeat it for the sake of clarity, right? It's there that I've written in the orange. So it's going to increase. Why? Because first step is when we remove the resistor in parallel, our total resistance goes up. When total resistance goes up, our total current goes down. When total current goes down, my V lost is going to go down. When V lost goes down, I've got more voltage to go out, right? And when my voltage goes out, increases, my V external increases, this V1 goes all the way up. Guys, thank you so much. That is me for today. We've got 5 minutes left for any questions. If you guys have questions on TikTok, please post them there in the chat or even on Zoom. I'll give you guys these 5 minutes to post. But thank you guys so very much for joining the session. Thank you for all your interactions. They make the lessons really, really worth it on my side. Looking forward to engaging more. Don't forget, tomorrow we've got a lesson on calculus where Tepang's going to be taking us through that section there. It's going to be an awesome one. Don't you dare miss it. And then don't forget, please, if you're on TikTok, follow us right now, share our page, go watch more of our videos. Even the guys on Zoom, go to our TikTok. It's at the Learning Space ZA. Go watch all our videos. We do all of this just to get you guys to pass. That's really all we want, right? We want the African child to pass. Go do well, guys, and make sure you nail it. I'll wait a few minutes to see if there's any questions. If not, you guys can do well. Thank you, Tabile, for saying you guys appreciate it. We appreciate you guys for coming to watch. Cass says, thank you guys for that. Judith, what time tomorrow? Tomorrow we are starting at 6 p.m. up until 8 p.m. There's a question saying, when are we going to do electrodynamics? Give me a second to check for you. I'll tell you just now. Let me just check my timetable. Bentley says, I'm confident I'm going to nail it. Thank you so much for me and the team. Yeah, thank you guys for us and the team. Remember, it's not just myself here in front. Thank you to Zapang, who does the math sessions. And there's another team of people behind the scenes who help us prepare these sessions, who help us put everything together. So thank you very much to the Learning Space team, to the Toe Institute team. You guys are wonderful. You guys rock, and everyone appreciates it.